Let's have our lecture video in integral calculus with the topic Application of definite integral plane areas by integration in rectangular coordinate. Now, let's consider this drawing here. If we want to solve for the area bounded by this curve here, the blue curve here, the x-axis and the y-axis, and this line, green line here. So we will be taking the area of this portion. Then we will use integration. So how do we use integration in solving for the area of this region? Now take note of this area strip. So we have there a vertical rectangular area strip with the area y dx. So having derivative of a is equal to y dx, we will integrate that and arrive at the integral of y dx, of course this one here, and the lower limit x1 and the upper limit x2. Now in this video, we will also learn how to get the limits, the lower limits and the upper limits. How do we arrive at the x1 and x2? Now take note that the area strip is vertical and it has the length y and the width is dx. The width is always in derivative form. So if we are using the horizontal area strip, we are to use the horizontal area strip. Okay, so the area of this is x dy. Okay, so that's how we put area strip. Now going back to the formula, how do we know if the limit is x and y? Remember that the vertical area strip here has the width dx. If we have the width dx here, therefore we have the limits as x. If we have the width as dy, if we are using area is equal to integral of x dy, therefore our limits are y1 to y2. Okay, so we can use this if our width of the area strip is dy. Okay, now why x1 and x2? Why the limits are x1 to x2? Now we will not just point any point in the coordinate plane. The reason why we have x1 to x2 is that if you put a scanner, it's like you're going from x1 to x2. So that's the limit. The lower limit is x1 and the upper limit is x2. Now how about for the second formula here, the y1 x dy. Now, if we are looking at this figure, this area, this is our area strip, x dy. If we are looking at that area strip, our limits are obviously the higher limit here at the end of the boundary, the intersection of the line and the curve is y2. So it's obvious that our upper limit is y2 because that's where the line and the curve intersect and it's the highest point. So take note, it is the highest point at where the boundaries intersect. Now how about the y1? It is the lowest point at where the boundaries intersect. So the lowest point at where the boundaries intersect are the point of origin. It's not this point here. It's the point of origin. The lowest point at which your boundaries intersect, which is the x and y axis. Therefore, if we write this limit here of the second equation, the second formula, becomes 0 to y2. So that should be the area of the figure if we're using the horizontal area strip. Okay, we will learn more. Let's go to the second figure. We have here the integral with negative integrand. So why negative integrand? The reason is, if we are looking at this area strip here, the area strip of x dy, since it's located in the second quadrant, therefore, the x is negative. So it's this formula that is being used for the horizontal area strip. It's the negative x dy. And then, since we are using the width of the area strip as dy, therefore the limits are y1 to y2. Looking at the figure, if our limits are y1 to y2, our y1 here is, so again, defining the limits are, the lower limit is the lowest point at which the boundaries intersect, and the boundaries here are the x-axis, okay, the x-axis, the y-axis, and the curve. So those are the boundaries, and we are considering this area here. So our limit now here for this figure is y1 is equal to 0, so here, up to the highest point at which the boundaries intersect, and that is y2. Next, if we consider the vertical area strip. If we are considering the vertical area strip, y dx, so this is the y dx, having the width as dx, therefore the limits are x1 to x2. Again, lower limit is where the lowest and the farthest. We are considering the y limits, lowest and highest. If we are considering the x limits, they are the farthest. So for x1, it's the farthest to the left where the boundaries intersect. So it's this point here. So x1 is x1. Then for x2, it's the farthest point at which the boundaries intersect, farthest to the right. So it's the x2, this point. Okay, so that's how we get the limits. Okay, more on that. Let's practice getting the limits. Okay? So we're done with x1 and x2. The reason why we're done with x and y, the x, and the reason why we have the vertical and horizontal area strip, and it's simple here. It's just area is equal to integral of y dx. It's because the boundaries are the x and y axis. Then it touches the boundary of a curve or a line. But how about if we are looking for the areas bounded by lines and curves, or bounded by curves? So how do we get the area? Now here, looking at this figure, we have two boundaries. We only have here two boundaries, the curve and the line. The curve and the line. These two boundaries intersect at 2 points, x1 and x2. So using the vertical area strip, so we're using here vertical area strip. So area now is equal to integral of y dx. Since we're using dx, we have the limits x1 to x2. But why is it that in this formula, it's y upper minus y lower. The y here becomes y upper and y lower. Why? It's because the vertical area strip does not touch the x and y axis. It touches the curve and the line, which both have equations. So the y upper here, the y upper pertains, or it's about the line. So the upper, which is it touches the line, so the equation of the line. Then the y lower, so the vertical area strip is touching the curve at the lowest point, or at the low point. So this is now the curve. YL, or y lower. Then as for the limits, we have the x1 to x2 limits. Okay, so that's how we arrive to this formula. Now the question is, will we use the horizontal area strip? If we are using the horizontal area strip, so I will take a representative area here. Okay. So this is dy dyx. Now I will tell you why we are not using the horizontal area strip here. It's because if we are using here y dx, so I will put here area is equal to integral of so this is x dy, so it's x dy. The limits are y1 to y2. Area is equal to, since it's touching the line and the curve, so x right minus x left dy y1 to y2. So that's the formula. The reason why we're not using it is because of the limits. The reason is the limits. The limits are y1 to y2. Notice that if you are using a scanner here, so from the lowest to the highest, so the lowest here is not y1, it's y2. So we will erase it. It's not y1 to y2, rather it's y2 to y1. So y2 to y1. And then if you're using a scanner, you're starting from y2 to y1. So this is your scanner here. Therefore, the area covered by your limits is only this portion of the curve. That portion only. Now, how about the rest? How about this portion here? It's not included in the calculation. That's why we're not using the horizontal area strip. There's another reason why we're not using the horizontal area strip here. It's because if I continue the area strip here, it will have a horizontal area strip at this portion here. This is dyx. Now this area strip here is touching the curve, the boundary curve at 2 points, and it means it will become 0. Why? Because if you remember, x right minus x left, and you're touching the same boundary, which is the curve. Therefore, this equation here for x right is the same as the equation for the x left. If you subtract it, then the answer will become 0. Okay? So that's the second reason why we are not using the horizontal area strip here. It's because the area strip touches the one boundary of 2 points. So what we learned here is that the area strip should touch boundaries once only. It should not touch any boundary twice, because the resulting equation will become 0, or the resulting area will become 0. Okay? So that's for this figure. Let's go to the next figure. So again, it has two boundaries, the curve and the line. Then it has a horizontal area strip of dA of x dy, or that is integral of x dy. And since we're using dy, the limits are y1 to y2. It is correct because y1 is lower than y2. And the limits are correct because it touches it is the intersection. It is the highest intersection of the boundaries and the lowest intersection of the boundaries. So here it is correct. This formula here is correct. Then we have x right. So x right here minus the x left. X right is the equation of the line, and then x left is the equation of the curve. Okay, that's correct. Now how about the vertical area strip? Are we using the vertical area strip here? If we are using the vertical area strip, the same happens with this case here. If we are putting here the vertical area strip of y dx, area is equal to integral of y dx, then x1 to x2. So area is equal to integral of y upper minus y lower dx, x1 to x2. We are not going to use the vertical area strip because of the limits. Why? Because the limits are x1 to x2. So meaning, it will just consider this area here. It will only consider the area at this portion. But as for this area, no, it's not being considered. Now if we try to get that using vertical area strip, so y dx, therefore it touches again the boundary on 2 points, and the resulting area will become again 0. So let's stick with the horizontal area strip. Let's go to the other figures. We have here area bounded by curves. So we have two curves. We have here the curve 1. Then we have the curve number 2. So the area strip used here is integral of y dx with limits x1 to x2 because we are using the x. Then as for the length y, we have here y upper minus y lower. And the limits x1 to x2 is correct because it is the intersection of the boundaries, the farthest to the left and the farthest to the right. And it covers the entire figure. And that is correct. Then we will not use the horizontal area strip, again, it's because it will touch the boundary on 2 points, or the resulting area will become 0. How about this one here? So we are using the vertical area strip of y dx. The limits are x1 to x2, or rather it is the origin, the farthest, because the boundary here is the curve and the x-axis. So the farthest and then the farthest. This is x. We cannot use again the horizontal area strip here because it will touch the boundary, the same boundary on 2 points. So it's a no for the horizontal area strip. How about here? Two similar figures of two different area strips. So we have here the curve. The boundary here is the curve, the x-axis, and the y-axis. So we're considering this area. Then we are using the vertical area strip, that is y dx, having dx as the width. So we have x1 to x2, or since it is the farthest to the left in the intersection of the boundaries, and then we have farthest to the right of the intersection, then we have here 0 to x as the upper and lower limits. Now for horizontal area strip, we have here y, that is x dy. So x dy, therefore, we are using the y1 to y2 as the limits. Now for the limits for y1, again, for the y1 or the lower limit, it is the intersection of the boundaries that is the lowest. And we have it as y is equal to 0. So that's why we have 0 here. Then for the upper limit, it is the farthest, it is the highest intersection point of the boundaries. So we have there y. Okay, so that's how we get the area strip, how we determine the area strip to use, and the upper limits and the lower limits. Now let's practice solving these examples. There are 4 examples for this video. For number 1, find the area bounded by the curve y is equal to 9 minus x squared and the x-axis. Solved in 3 ways. Now, if you notice, there is no graph here, so meaning we need to sketch the graph first. So we need to sketch the graph. Now, if you recall how to sketch a graph, so let's just draw here. Okay. So if we have here the we put here the y and the x using the okay. Using this equation here, y is equal to 9 minus x squared. If we substitute the value of x as, if we substitute the value of, we substitute the value of y as 0, we can get the value of x as either 3 or negative 3. It's because if you do have it, 0 is equal to 9 minus x squared becomes x squared is equal to 9. Square root of 9 is negative 3 or 3. Okay. Next, we have here, if we put x as 0, the value for y is 9. Okay. And then, if we put here, if we put x is equal to 1, the value for y is, okay, let's continue this one here. Okay, so if we put here, so y is equal to 9 minus, if we put the value of x as 1 squared, therefore, or 1 or negative 1, so if we put the value of x as positive or negative 1, the value of y is 8. If we put x as positive or negative 2, so positive or negative 2, that is 9 minus 4, that is x is equal to 5. If we put the value here, I think that's enough already, okay? So let's just sketch the curve. Sketch the curve here. So there is no negative value for y, therefore it's either the first quadrant or the second quadrant. So we have here, if we put here negative 3 and then 3 here, and then this becomes 3, 6, 9. This is y, this is x. So if we graph the point, this is 3, 3, we have here 9, 0, and we have 5, 2, 5, 2, it will be around here, and 8, 1. So the resulting figure is parabola. So we have here a parabola wherein it has the equation y is equal to 9 minus x squared. Right? And then the points here, the limits are, we have here negative 3, so negative 3, 0, and then we have here 3, 0. We can solve this in 3 ways. Sixteen problem solved in 3 ways. For the first solution, let's have the first solution here as using the area strip vertical. Oops. If we want to use the vertical area strip, it should be touching the curve. So we have here y dx. The area strip is y dx. Therefore, area is equal to integral of y dx. Since we are using dx here, the limits are x1 to x2. So if we have here, if we are using the general one, so y upper minus y lower, dx x1 to x2. So we have here area is equal to integral of y upper. Y upper is the curve. So that is 9 minus x 9 minus x squared minus the y of the lower, which is y is equal to 0. So this is dx. The limits are from negative 3 to 3 for the x. Let's just put it. So So that is negative 3 to 3. Now what we have learned from the last video about definite integral is that for the long method, okay, for the long method we have there, we integrate this as 9x minus x raised to 3 over 3. Then evaluate it with the lower limit negative 3 to 3. So that is, just substitute 9 times 3 minus x, or that is 3 raised to 3 divided by 3 minus 9 times negative 3 minus negative 3 squared over 3. So this is the long method. So this is 36 square units. Okay. So just like in the previous video, we have learned to use our calculator here in definite integral. So we can use also our calculator here. Let's find calculator first. Okay. Oops. So we just have here input integral of. So we have here parentheses. So we have 9. So we are going to use this equation here. So we have parentheses of 9 minus alpha x squared. Then, oh, it's already. Close it with parentheses. So we have here negative 3 to 3 equals 36. So we have the correct answer. Now for the second solution. So this is the first solution, taking it as the whole figure, the whole area. So that's why we got the boundary from the farthest to the left, then farthest to the right. We have the second solution. Okay, we have here, let's use this figure here. For the second solution, we will consider half of the parabola. Using area strip of vertical area strip, this is y dx, we will be considering just half of the parabola. That means the boundary that we have will be this point here up to this point. So our boundary is this one here to this point only. So vertical area strip, area is equal to y upper minus y lower dx x1 to x2. So the area here is, that is 9 minus x squared minus 0 dx. Our x1 is 0 to 3. Now since we are considering half of the parabola, the area therefore here is twice of the result of this area. So again, let's use the calculator. So using this area, but the difference is the limit. Let's use the limit as 0. Equals 18 times 2, 36. We have 36 square units. So that's the second solution. The third solution is Using again the same parabola. Third solution. Half area again. Consider half area. We will consider the half area because we are using the horizontal area strip. Why half? Remember that if we use the horizontal area strip here, it will touch the boundary on 2 points and the answer will become 0. There is a solution to that. The solution to that is taking or considering the half only, so that your area or your horizontal area strip will touch 2 boundaries. You will be touching the curve and the y-axis. Now, this is dy x. So we have here area is equal to integral of x dy y1 to y2. Area is equal to integral of x right minus x left dy y1 to y2. Since we are considering half, let's put here 2 times the integral of, what is the x right? What equation are we going to use? If this curve here has the equation y is equal to 9 minus x squared, x is equal to 9 minus y raised to 1/2. Therefore, our x here becomes 9 minus y raised to 1/2 minus x of the left, which is 0. Of course, this is x is equal to 0, the y-axis. And this one, dy. How about the limits? Again, if we are using y1 to y2, y1 is the lowest point of intersection of the boundaries. So this is also a boundary, the x-axis. So the y there is 0. The highest intersection of the boundaries, we have there the 0, 9 there. So y2 is 9. So area is now equal to, again, let's use our calculator. If we are allowed the calculator, then use the calculator. But if you're not allowed, then at least you know how to use the long method that we have discussed in the previous video about definite integrals. Okay, so type in 9 minus y or alpha x raised to the power of 1/2. So arrow, we have there 0 to, oops, so this is 0 to 9 equals 18 times 2, 36. 36 square units. So all 3 solutions leads to the same answer. All 3 solutions provide ways on how you use the area strip, on how you derive formulas in order to solve the area of this figure. So this is for your number 1. Screenshot first. So all you need to do is to sketch and then solve. Let's go to the next example we have here. Find the area bounded by the curve y is equal to x times x minus 1 squared, the y-axis, and the line y is equal to 2. Again, we will be sketching here the curve first. So this is y and then this is x. Using this equation, so if x is equal to 0, y is also equal to 0. If x is equal to 1, so what is y is equal to 1 times 1 minus 1 squared? Y is equal to 1. This is 0. So this is already 0. So y is equal to 0. If x is equal to 2, so that is 2 times 2 minus 1 squared. So that is equal to 2 times 1 squared. So y is equal to 2. If x is equal to 3, if x is equal to 3, therefore this is 3 minus 1, that is 2 squared. 4 times 3, this becomes 12. If okay, so let's try to sketch that. Let's sketch here. Okay. So we have there 12. So first we have the 0, 0, 0, 1, 2. Okay. How about negative 1? If we put here negative 1 for the x, y here is negative 1, negative 4. So we have here negative 4. So negative 4, 1. So we have here this point. Okay. So point, then 0, then 2, 2. So if this is 4, negative 4, therefore 2 will be here. And then 3, 12. So where is the boundary? This is the curve, right? The blue line is the curve. This is the y-axis. Then the line is y equals 2. Okay. This is the curve. And then the line is y is equal to 2. This is the line. Okay. So we have here the boundaries. The line is equal to 2. The curve is y is equal to x minus 1 squared, and the y-axis. So the area to be considered is this portion here. So let's have the vertical area strip. First, let's try the vertical area strip. So this is dx y. So the boundaries are the point 0, 0, the origin, point of origin, and then this point here. What point is that? That is 2, 2, point 2 and 2. Okay, so let's solve for the vertical area strip of y dx. Since we are using dx, the limits are x1 to x2. Area is equal to integral of y upper minus y lower dx x1 to x2. So that is equal to our y upper, the upper line here, the upper point that is connected to the area strip is the y is equal to 2. So this is 2 minus the lower. Y lower is this point here. It touches the curve. The curve has the formula x times x minus 1 squared. I'm using double. Oops. Dx. Then x1, the farthest to the left, that is 0. The farthest to the right, that is 2. So area now is equal to. So let's use our calculator. So we have here 2 minus alpha x times alpha x minus 1 squared. Then we have 0, 2, 2 equals 3.33 square units. So that's the area. Can we use the horizontal area strip here? Let's try. We're going to use the horizontal area strip. What will happen? So imagine this area strip here as horizontal. We put, that becomes dyx. So area is equal to integral of x right minus x left dy. y1 to y2. Can we use the horizontal area strip? The x right will come from the curve. The curve has the equation y is equal to x minus 1 squared. Use implicit function and put the x solo on the left side. So it's quite complicated, isn't it? It's going to be complicated and it will take longer to solve. So since we were able to solve for the area using the vertical area strip, then we can just stop there. So we're just using the vertical area strip and not the horizontal area strip because it will consume a lot of time. This is the easier one, so go for it. And besides, the problem did not mention to solve in 2 ways. Rather, it just says there, find the area. So since you were able to find the area, then that's the solution. That's for number 2. Let's go to number 3. Find the area bounded by the curve 2x squared plus 4x plus y is equal to 0 and y is equal to 2x. Again, let's sketch the curve. Oops. So we have here y and x. So using this equation here, if we have the value for, okay, so that's, this is 2x squared plus 4x plus y. This is y is equal to negative 2x squared minus 4x. If we have the value of x as 0, y is also equal to 0. If we put the value of y here, of x as 1, so let's see, y is equal to negative 2 1 squared minus 4 times 1. So y is equal to negative 2 minus 4 is negative 6. Next, if we use the value of x as negative 1, y is equal to negative 2, negative 1 squared minus 4 times negative 1. So this is equal to negative 2 plus 4. Y then becomes 2. If we use the value of x as negative 2, so y is equal to negative 2 times negative 2 squared minus 4 times negative 2. So y is equal to, this is 4, so negative 8, positive 8, so y is equal to 0. Now we can do this on and on, but what we're interested in is that where will they intersect with the line y is equal to 2x. The faster way to finding the answer to that is, so intersection. For the intersection, we have there y, so we have here 2x squared plus 4x plus y. So this y here becomes 2x equals 0. So 2x squared plus 6x is equal to 0. So x is 2x plus 6 is equal to 0. Cancel x is equal to 0 now. So 2x plus 6 is equal to 0. 2x is equal to negative 6. X is equal to negative 3. So the intersection point is at x is equal to negative 3. Substitute that to the equation. Y is equal to 2x. So y is equal to 2 times negative 3. Y is equal to negative 6. Therefore, point of intersection is at 0, 0. Because of this, we have there x is equal to 0. And negative 3, negative 6. So those are the points of intersection. So let's put here negative 3, negative 6. So we can now sketch the curve. So looking at the points here, they're mostly at second and third quadrant. The second and the third quadrant. I'm curious about the line, where since it's a line, so let's just leave it as it is. So we have here, okay, so this is point 0, 0. This is y and then x-axis. Let's put here 2, negative 2, negative 4, negative 6. Then we have here negative 2, negative 4. So the line here is intersecting this point, and then negative 3, 6. So at this point here. Also, we have the curve. Okay, Okay, so let's put blue line for the curve and green for the line. So for the curve, we have here the points. So we have y negative 6 is equal to 1 here. Then we have 2, negative 1. This point here. Then we have y is equal to 0 at x negative 2. Okay. Right? So we have the curve as pointing this way. So here's our curve. Then our line is here. There you go. So this is line 2x, and this one here is the curve y equals negative 2x squared minus 4x. So remember in the note here, it kind of looked like this one, but it's just inverted. So what area strip are we going to use here? The clue, we're not using the area strip that will possibly touch the boundaries on 2 points. That is the horizontal area strip. So we're not going to use horizontal area strip. Instead, we're going to use the vertical area strip. Again, the problem says here to find the area only. Does not mention finding the area on 2 ways. So this is y dx. Of course, I'd be happier if I could solve this the faster way. So area is now equal to y dx, x1 to x2. So this is y upper minus y lower dx, x1 to x2. Our limits here, our boundaries. So this is negative 3, negative 6, 0, 1. Therefore, we have here y upper touches the curve. So the y upper here is negative 2x squared minus 4x minus the y lower touches here the line. So 2x dx, x1 the farthest to the left, negative 3, x2 the farthest to the right, 0. So area now is equal to clear this one. Then we have here negative 2 alpha x squared minus 4 alpha x, close parenthesis, minus 2x, 2 alpha x. Limits are negative 3, then upper limit 0 equals. So the answer here is 9 units. 9 square units. Okay, so that's the answer. Again, if calculator is not allowed, then you must show your solution, the long method, meaning you just have to integrate this one by one and then substitute the upper limit minus the lower limit. Practice that also in case calculator is not allowed. Now so this is number 3. Screenshot first. Let's proceed to the last problem, number 4. Find the area bounded by the curve y squared equals 2x plus 3 and y is equal to x. The parabola y squared equals 2x plus 3 and the line y is equal to x. So let's sketch the parabola first using the equation y squared. So y squared equals 2x plus 3. Okay, so we have here y and then x. If we put here, so I think it's easier if we use x. So x is equal to y squared minus 3 over 2. If we have the value of y as 1, so x is equal to y is equal to 1 minus 3 over 2. So y is equal to 1, therefore negative 1. So if y is equal to 1, x is equal to negative 1. Okay. Now if we use here if we use here y is equal to 0 minus 3 halves minus 3 over 2, therefore x is equal to 1.5, negative 1.5. Then if we use here the value of y as 2, so x is equal to 2 raised to 2 is 4 minus 3 divided by 2, x is equal to 1/2. So if y is equal to 2, x is positive 0.5. Okay, so let's find the point of intersection. Of the two boundaries, the line and the curve. So y squared equals 2x plus 3. If y is equal to x, so x squared is equal to 2x plus 3. So we have here x squared minus 2x minus 3 is equal to 0. Therefore, we have here x minus, because we have here negative 3, 1. So we have there x minus 3, then x plus 1 as the roots. Or you can just solve this using the quadratic equation or the calculator. You can use that. So we have here x is equal to 3, x1, or the first point. Then x2 is equal to negative 1. Substitute. If y is equal to x, therefore point of intersections are 3, 3 and negative 1, 1. Negative 1, negative 1. So that's the point of the line also. Okay, let's sketch that. So from the looks of it, so let's use the all quadrants. So we have there we put here negative 2, 1, negative, this is 1, 2, 3, this is negative 1, negative 2, negative 3, negative 1, negative 2, this is 1, 2, 3. Okay, so let's find the boundaries for the curve. The curve here is 1, negative 1, 1, negative 1. Wait, so since y is squared, therefore this is positive, negative, positive, negative. Okay, so y is these points. If y is equal to 0, therefore this is the point. Then positive 2, negative 2, we have here the points. Okay, so we have here also the line. The line has the points 3, 3, 3, 3. Then negative 1, negative 1. This point here. Alright, therefore, let's sketch the. So this is the line. Then we have the curve. Parabola. Alright, so I have a problem with my sketching, but the point here is we get a picture of how it looks. So there you go. We have here the boundary of the curve. So this is curve x is equal to y squared minus 3 over 2. Then this one here is the line. Y is equal to x, or x is equal to y. Coordinates, the point of intersection 3, 3, and negative 1, negative 1. So the area strip that we can use here is, can we use vertical area strip? Take note of this portion here. So if we use vertical area strip, it will touch both boundaries, or it will touch the boundary on 2 points. So no, it's a no for the vertical area strip. So let's proceed with the horizontal area strip, which is the easier one. So dy x, so area is equal to integral of x dy y1 to y2 because of dy. So area is equal to integral of x right minus x left dy y1 to y2. Now this is equal to x right. So the area strip is touching the line. Therefore, we will put here the equation of the line. X right is y minus the x left. The area strip is touching the curve on the left side. So we have there y squared minus 3 over 2. The x of the curve, dy. Then for y1, the lowest. So for y1, we have the lowest point of intersection, negative 1. The y2 is the highest point of intersection. We have there 3. Therefore, we now have the area. So alpha x minus alpha x squared minus 3 over 2 The lower limit is -1 and the upper limit is 3 equals. So the answer there is 5.33. So area is equal to 5.33 square units. So that's for number 4. So that's all for for this video. So this is the last one, number 4. Okay. So again, I advise that you still practice how to solve the long method. In case, again and again, in case calculator is not allowed, or if you didn't bring your calculator with you, then at least you can still solve the area using the long method. And the calculator will just help you to see if your answer is correct.